Hello, welcome to our peer-to-peer blockchain network for ECE 4960. We are Team 3 and we worked alongside GE to make this project. This team consists of Danny Zhang, Jason Brantley, Matthew Long, and Russell Zimmerman. As technology continues to advance every single day, companies are looking at new ways to protect their data against this growing technology. Our project focuses on using blockchain technology and peer-to-peer network to serve as a decentralized framework application for data auditing and logging. We began our project by looking into existing blockchain-based approaches, example cryptocurrency. Following that, we looked at different network protocols to see which best suited us. We focused on the main three issues that we had at hand: scalability, security, and real-time processing. Our project charter was to develop an application to demonstrate the implementation of a privilege/permission distributed ledger for auditing. This auditing can be done for GE employees, vendors, customers, and auditors. Logging changes made to a system configured with a peer-to-peer network of ICS equipment was demonstrated using small, scalable, and cost-effective devices by April 21st. This was showed in our project by using 3 Pis and a laptop. For our high-level overview, we have a block diagram consisting of 5 different blocks: the turbine ICS at the customer site, the Raspberry Pi, the blockchain network, the GUI for service and application, and the cloud database. For example, the turbine would send information to the Raspberry Pi. From there, the Raspberry Pi would be able to communicate back and forth with the blockchain network, and the blockchain network being able to communicate back and forth with the cloud database to store all the information. From there, a customer or GE would be able to view through the GUI interface the blockchain network to see if any changes were made. Information needing to go back and forth between all 4 of those different blocks is quite critical because in a blockchain network, you constantly are searching for different nodes, sending and receiving to those nodes, deciding which is nodes is the miner, and selecting the miner.
So this is a sample database that we made in our AWS RDS. This is a centralized database, but we're just using it as a testing ground for our peer-to-peer network to see if our pipes can connect, grab data, hash it, put it on a blockchain. That's all that's for. Coming up, we have a video of that happening.
Okay, here we have an interface to our database. It's a GUI developed in Python. So I've changed a few settings, the device settings 0 through 5. And here, when I click change database, we're gonna see that the database, after being changed, sends a signal to the nodes, and then the nodes start performing the miner's algorithm. So these colors don't mean anything right now, but will be explained later.
For our hardware design requirements, we use a network of blockchain nodes, which consists of 3 Raspberry Pis and a laptop connected in a peer-to-peer Wi-Fi network configured to run the blockchain Python script. Each Raspberry Pi is connected to an RGB LED, serving as a simple human-machine interface. To begin our higher level algorithm, first, the device data is changed in the database, which activates the miner selection algorithm on the peer-to-peer network. The result of this selection algorithm is saved to the local blockchain in the Excel file and is also sent across the network to other devices. For our change detection algorithm, this operates either with a change or on a timer. This then selects a miner selection algorithm, and if the miner selection algorithm is successful, a new block is broadcasted. If it is not, the process repeats. If a new block is broadcasted, that new block will be added to each device's local blockchain, and the process will repeat.
So this is the miner selection algorithm as discussed with Dr. Yu. So let's say we have two nodes for this example, node 0 and node 1. So node 0 and node 1 will both generate a random number, 123, 321, and they will create a hash of that number. And then node 0 will send to node 1, and node 1 will send to node 0 its hash and receive vice versa. and then node 0 will send the original number to node 1 and receive the original from node 0. And then we verify and calculate sum of these two numbers, which adds up to 444. And then modulate it by 2, which gives us the remainder 0. Now, for example, if this number was 441 and we modulate by 2, it will give us 1 remainder, which then node 1 would be the selected minor instead of node 0, as in this example. So this is a minor selection video where we're showcasing the start of the minor selection algorithm. So as you can see, red means that the pies are searching for nodes, and in a few seconds here, we can see that two of the lights turn blue, while one of them is still red. Let's give it a few more seconds here. And as you can see, all three lights turn blue, and then it's going to eventually turn green. But why there is a delay is because it's a small little feature I added where whichever node initiates the minor selection to sync with all the other nodes stays on that light just a few seconds longer, so we can most of the time diagnose issues or stuff. But this is not a necessary feature. But as you can see, it turns blue. That means it's sending and receiving data to and from the other nodes. And then in a few seconds here, it should turn green. That node is still delayed because it was initially the first node to send out the my selection signal. But if we go back just a little bit here, as you can see, it was a little bit quick, but you can see the LED flash purple and then off, signaling that this is the node that was performing the mining and adding a new block and sending the new block out. But that is the video for a single run here. So next up is the discussion implementation. So the application consists of 5 different primary segments. So the first segment is the configuration file. So the configuration file defines the IP ranges that the nodes on the network is allowed to connect to. So this design choice that we have for a static IP table is similar to what a normal peer-to-peer network has. We tried to use a way to search for devices, but one of the biggest problems is how big the Clemson network is. We have thousands upon thousands of different subnets, IP addresses, and it was just taking way too long to search through them. Below that is the AWS MySQL server credentials that we use to connect to the AWS server. Nothing special there. And after that, we have database and data frame. In this case, data frame is referring to the Excel file blockchain.csv. And the database is referring to the blockchain itself that's stored on a library called Plivo. Plivo is a branch of LevelDB. LevelDB is a key value blockchain storage that is also used by Bitcoin, and it seems very easy and very secure. After that, it's just a for loop to get the most recent block on the blockchain. Nothing special there. And then this is just our RGB controller to set different colored lights. This is the node. I'm gonna avoid talking about network. That would take too long. But the gist of the network Python class is that it stores multiple nodes, and it is the one that initiates the minor selection algorithm and various other messages that send across between nodes. But this class node has very important details inside of it. It has its own IP port, the random hash, and the random num that's generated in the minor selection algorithm. And then here's the most important part of the implementation is the block. The block stores a variety of information. Index is the block number. Timestamp is when the block was mined. Sender is who sent this block. Uh, who and device go hand in hand. Who and device are basically who made a change to the database and what device they used to do it. Previous hash, as I explained before, is just a previous hash is a previous block. Database hash is pretty self-explanatory, and then block hash is the hash of the entire block here, which in this case is ending before the block hash, so database hash, previous hash, and everything. So in this video, I showcase the outputs of each server. Well, this is only for the laptop that is running the application. But if you look at the video here, I'm just gonna pause it real quick. But you can see how it's sending messages, is adding, and is selecting the miner. This is a pretty simple idea here. And then at the end here, you can also see the blockchain in CSV format, where you have index, timestamp, sender, etc., as previously mentioned in the block class.
One strength of our project was the overall simplicity of our hardware configuration. To be specific, our Raspberry Pis did not require a whole lot of hardware configuration. This was great for us because we did not have a lot of room to make an error with the hardware. Another thing that was a strength for us was our overall availability. Our group attended all meetings, and most members did not miss a meeting. However, one weakness would be our communication. I feel that our communication with GE and with each other could have been a little better earlier on in the semester. Furthermore, we were also a little late in communication some nights, and this caused members to miss a couple of information meetings.
For the future direction of our project, we see this firstly being implemented at the customer site and being sold to them as a product. This project was initially designed for this use. This is because customers now have a secure way to track all their data from any malicious attackers or any malicious employees to know when it happened and who caused this to happen. Secondly, we see GE implementing this themselves to log their changes in the ICS systems. Finally, any data synchronization and implementing a way to transfer current blockchain to a new node on the network.
So that's about it. Here are some references that made this possible and some acknowledgments I would like to go over. First of all, thank you to Dr. Raza for his incessant help throughout the project. He was available whenever. We emailed him in his office, in the Senior Design Lab. Thank you to Dr. Yu for helping us solidify our understanding of all the technical aspects of this project, including providing us with a lightweight mining algorithm. Thank you to the people at GE. It was a wonderful tour that we went to, and thank you to Mr. Gary and Mr. McCune for helping us throughout this project with understanding the big picture.